Hey, we're going to talk about machines today. Machines are things that we use to either make our work easier or safer. A simple machine is what we're going to focus our attention on, and the definition of a simple machine is that it will perform one action. Some of your information will say that it's a machine with only one moving part, but there are some machines that have no moving part. So it's more accurate to say it performs one action. Now we're going to measure simple machines by talking about the mechanical advantage of the machine, and we abbreviate that as a MA. Mechanical advantage is a ratio between what I do on the machine and what the machine does for me. So if the mechanical advantage is greater than 1, we would say that it makes the job easier. If the mechanical advantage is less than 1, it would mean that the job is harder. Now, you may think that a machine that has a mechanical advantage of less than 1 would not be useful, but there are machines that we want to make life more difficult for us. If you think about exercise equipment, you want that machine to make your muscles work harder doing the same job. So a low mechanical advantage is a good thing. There are some jobs that we would prefer to work harder to do as long as it means that we'll be safer. If you think about rowing a canoe, I might want to be in this pond, but the pond water's too cold. So I can't be in the water, it's not safe, but I can row in the boat even though it takes more energy to row the oars than it would to just swim in the water. It's safer. We have two formulas that we're going to use for mechanical advantage. We have the force ratio, FR divided by FE. And if you see down here, FR stands for the resistance force, which we a lot of times refer to as the load on the machine. It could also be considered the weight of the object, whatever the machine is lifting for you. The effort force is what you do to make the machine work. So I like to say that FE is me. It's what I do for the machine. MA is DE over DR. This is distance. When we're talking about machines, we're going to look at force, how much force I put in, and how long I have to apply that force. Now, DE is the effort distance. That's us. And the longer we have to work, the less force we'll have to put in. So more distance is a good thing. DR is the resistance distance, and it's what the machine does. It's how high the machine lifts the object we're trying to lift, or it's how far it moves it. So DR is the machine, and DE is us, or DE is me. Now we have levers. Levers are a rigid bar that pivots at a fixed point. Now, that fixed point is called a fulcrum. We have 3 different classes of lever, and all of these are simple machines, but they work a little different. The first class lever has the fulcrum. This purple triangle in each of the pictures is the fulcrum. In the first class lever, that fulcrum is in between my effort force and my resistance force. Now, because it's in between, some students would like to say that it's in the center. It doesn't have to be in the center. It just has to be between the two. If you think about a crowbar, it pivots much closer to the barrel when you are putting your weight at the other end. So it's not always in the center like in a seesaw situation. The important thing is that it's between the two. In a second class lever, the pivot point and the person using the machine are on opposite ends. A good thing to help remember with this is a wheelbarrow is an excellent example of a second-class lever. If you consider the wheel as the pivot point and the handles are where I apply my effort, so when I lift up on the handles, it pivots on the wheel and then I'm able to use the machine. So this is a second-class lever. Notice that the weight or the load that the wheelbarrow would support is between me and the fulcrum. Now, it's not in the center again. It could be anywhere between the fulcrum and me. On the third-class lever, it's a little harder to understand. We have the fulcrum at the same end as my effort force, and the resistance is at the opposite end. Again, the effort force doesn't have to be between. It just has to, it doesn't have to be in the center. It just has to be in between. Now, the fulcrum with the effort at the same end. This would be like an axe. I'm holding it at one end and I swing it down to chop the wood. I'm holding it at the base of its handle, or a softball bat. I hold it at the base of the handle and then I swing so it rotates where I'm holding it. A fishing rod, a golf club, all of these things do this. You hold it at one end, it rotates, and the weight of the machine is the resistance force that does the work for you on the other end. Okay? Now, we use the DE and the DR when we're talking about the distances on these machines, and I have labeled in each of these pictures the DE in orange and the DR in pink to help you see where those distances are happening. In the first-class lever, it's easy to see that, the DE is on one side, the DR is on the other. But when you get to the second class and the third class lever, the DE and the DR overlap for part of their length. The DR is a smaller distance than the DE in the second class lever, but when you come over to the third class, they switch. The DE is the short one, the DR is the long one. Inclined planes are our next type of machine, and the definition of an inclined plane is that it's an object that moves along a plane from one position to another. That position could be from low to high or from high to low. It could be left to right. As long as it moves the position of the object from one place to another, then it is a machine. It's doing work. Now, we have three different inclined plane categories. We have ramps, wedges, and screws. The ramp is what you're used to thinking of as an inclined plane. You have your wheelchair access ramp, or the ramp to put the go-kart onto the trailer. We have a height and a length for this inclined plane. Now notice that the length is not the base of the triangle, okay? It is where I would be. If I were to walk up this inclined plane, I would do it along that hypotenuse, and we call that the length of the inclined plane. That's where I'm going to do my work. This is where the machine does its work. As I walk up that ramp, the ramp lifts me from a low point to a high point. Now notice the ramp doesn't move. If you look at the definition, a ramp is something that allows the object to move on it. It's built to allow us to go from one position to another. The work comes from its structure, not from anything on it that moves. Now when you get to a wedge, it's a little different. This time the wedge is going to move through the object. Now if you look at the picture and imagine that you're looking from the top down of an axe, maybe you can see that it has two lengths that will split the wood. The wood will split along both of those planes, and the wider my height is here, notice that because I have two L's, that's listed as 2H. We have two triangles back to back here. The wider this 2H is, the faster the axe could go through. Another way of looking at a wedge, or another example of a wedge, would be a knife. The knife cuts through steak or, your carrots or whatever you're cutting. And when you are using that knife, the edge that's sharp is very thin. And as it goes to the back of the knife, it gets thicker. Okay? Not as pronounced as this. Now, a screw. Obviously, a screw is a screw. But anything that has a spiral with threads on it would be considered a screw. So the drill bits, your jars on the lids, when you screw the lids on, those are considered a screw, a machine. And I know you've never looked at a screw as closely as this, but if you look at each thread on a screw, what you'll notice is on the very edge of the screw, it's very thin, and as it gets close to the base of the screw, it gets thicker. So, in essence, it is a wedge in miniature on each one of those threads. And so, as you screw this into the wood will split above the thread and below the thread in a spiral as the screw goes deeper into the wood. Alright, so that's the inclined planes. Notice that we still have our same formula, but we are going to talk about length over height, and length is the same as the effort distance, and height is the same as resistance distance. Okay? Now we come to our last two categories of simple machines. We have wheel and axle, and we have pulley. Now, I don't have a definition for you for both of these because I feel they are fairly familiar to you, but I'll tell you that a wheel and axle is two circles allowed to rotate as one. So I turn the wheel, and the wheel in turn will turn the axle. Now, notice that the wheel has this radius here, and the RW designates the radius. The axle also has its own radius. And when I want to calculate the mechanical advantage of a wheel, all I have to do is compare the radius of the wheel to the radius of the axle. And that will give me the mechanical advantage. Now the wheel is where I do my work, so that's DE. And the axle is what the wheel does for me, so that is DR. Okay? Examples of wheels, obviously, are wheels or a steering wheel. It could also be a doorknob. Anything that turns and has another thing inside it that it turns for you. All right, now we have pulleys, and pulleys also have a wheel type device, but the difference is that it has a groove on it that you put a chain or a rope or a belt through, and you pull the rope on that groove. Now, we have three different kinds of pulleys. We have a fixed pulley. You see that it's attached to the ceiling, so the rope moves, but the pulley doesn't. We have a floating pulley, which is also sometimes referred to as a movable pulley. And notice that the rope is attached to the ceiling, and I have the pulley, and the pulley is allowed to move. And then I have a block and tackle, or also called a pulley system. And it has multiple pulleys in it. I've drawn mine with 2 pulleys. It could have more, as long as it has more than one, and one of each kind. So the top is the fixed pulley, and the bottom is the floating pulley. That's what makes it a pulley system. It has one of each. Now, the calculating mechanical advantage for a pulley is a little different because I talk about the number of strands that pull up on the weight. If you notice in each of these pictures, I have this orange box. That's my FR. That's the weight of the object that I'm trying to lift. Well, in this first example, my effort will pull down on this rope and make the box go up, okay? There's one section of that rope pulling up, so my mechanical advantage is 1. On this next piece, I pull up and the pulley slides. An example of this would be like a zip line. You've seen zip lines in your movies that you like to watch. Well, as I pull, there's 2 pieces of string pulling up, so that has a mechanical advantage of 2. When you look at this third picture, I have 1 string that I'm pulling down on, and it pulls up and around. Well, there are 2 sections that will pull up. So again, a mechanical advantage of 2. Now be careful. A lot of students want to just count the number of pulleys and say, okay, if I have 1 pulley, that's a mechanical advantage of 1. That's not always true. Look at this one. I have 1 pulley, but its mechanical advantage is 2 because there are 2 sections pulling up. Also, some pulleys have more than 1 groove in them. So even if I had a situation like this, if I had 2 grooves in that pulley and I could wind 2 sections of rope from the box into my hand, I would have a mechanical advantage of 2 here. So you have to count the string, not the pulleys. All right, that's all.